30 separate model runs, 30 slightly different versions of the same ocean, each one nudged with a tiny variation at the starting line, then set loose to simulate the next 12 months of the Pacific. Not one of them disagreed. Every single run came back with the same answer: an El Niño strong enough to compete with the biggest events of the last 100 years. That's the July experimental forecast from NOAA's Geophysical Fluid Dynamics Laboratory. And if you've spent any time around seasonal forecasting, you know that kind of agreement is unusual. Models argue with each other. That's practically their job. When 30 of them stop arguing, it doesn't mean they're right. It means the signal underneath them has gotten loud enough that the small differences stop mattering. And this month's forecast came back warmer than last month's. If you want the Pacific explained without anybody trying to frighten you into staying, subscribe. That's the whole promise of this channel, and it's the only one I'll make. Here's what I want to do over the next 20 minutes. I want to walk you through the 4 numbers NOAA is actually watching, and I want to show you why one of those 4 is behaving in a way that made me sit up. I want to explain the mechanism, not the cartoon version, the real one, because the real one is more interesting. Then I want to tell you about something NOAA did in February that changed how every El Niño in history gets graded, including this one. Almost nobody is covering it. And by the end, you'll know the exact date in August when the next piece of this puzzle arrives, and you'll know what to look for when it does. Let's start with where the ocean actually is. On the 9th of July, the Climate Prediction Center in College Park, Maryland, issued its monthly diagnostic discussion. The alert status at the top of that page is not a watch. A watch means conditions are favorable for something to develop. This says advisory. An advisory means it's here. The headline sentence is short. El Niño continues and will strengthen through the end of the year, with a 97% chance it lasts through early spring of 2027. Sit with the shape of that number for a moment. Out of every 100 ways forecasters can imagine the next 8 or 9 months unfolding, 97 of them still have El Niño in the picture. Seasonal forecasting almost never gets to talk like that. Ask anyone who's tried to forecast a winter in August. Now the 4 numbers. Forecasters divide the equatorial Pacific into monitoring boxes, running roughly from the middle of the ocean eastward towards South America. The most famous one is called Nino 3.4, sitting in the Central Pacific. That's the box that defines the event. The latest weekly reading there was plus 1.2 degrees Celsius above average, a little over 2 degrees Fahrenheit. 2 degrees. That sounds like nothing, doesn't it? If your bathwater dropped 2 degrees, you might not reach for the tap, but you're not looking at a bathtub. You're looking at a stretch of open ocean, thousands of miles across, warmed top to bottom through a layer of water deep enough to swallow a skyscraper. 2 degrees, spread over that, is an amount of stored heat that has no comparison in ordinary life. It's the reason a temperature reading off the coast of Ecuador can change how much rain falls on Texas in January. Then there's the far eastern box, right up against the coast of South America. That one Nino 1 plus 2 came in at plus 2.7 degrees Celsius, nearly 5 degrees Fahrenheit above normal. That's not a subtle shift. That's the difference between water that makes you catch your breath when you step in and water that feels like a warm bath. Fishermen in Peru have been noticing that difference for centuries. They're the ones who named this thing. And then the 4th number, the one furthest west, Nino 4 plus 0.5 degrees Celsius, barely over the line. That's the number I keep coming back to, because look at the shape of it. Plus 2.7 in the far east, plus 1.2 in the center, plus 0.5 in the west. The warmth isn't spread evenly across the Pacific, it's stacked up against South America and thinning out as you travel west. Forecasters call that an east-based event, and it's worth knowing that the 2 largest El Niños of the modern satellite era, the one in 1982 to 83 and the one in 1997 to 98, both wore that same signature. That is a pattern, not a prophecy. I want to be careful here. A resemblance to 1997 is not a forecast of 1997, but when you're reading a developing system, the geometry tells you something the headline number can't. So how did the heat get over there? To understand that, you have to understand that for most of the time, the Pacific is holding its breath. Here's what I mean. Across the equator, the trade winds blow steadily from east to west from the Americas toward Asia. They've been doing it for as long as there's been an atmosphere. And because wind dragging across water pushes water, those trade winds spend decades shoving the warm surface layer of the Pacific westward, piling it up against Indonesia and the Philippines. That pile is real, and it's enormous. In a normal year, the sea surface near Indonesia stands physically higher than the sea surface near Peru, not by a little, by a couple of feet. The warm water there isn't a thin skin. It's a reservoir, hundreds of feet deep. And on the other side, off South America, the opposite happens. As the surface water gets dragged away, cold water rises from below to replace it. That cold upwelling is why the Peruvian coast has one of the most productive fisheries on the planet, and why the water there is startlingly cold for a place sitting on the equator. That's the inhale. Warm water held to the west, cold water rising in the east, held in place by wind. It's a balance, and like a lot of balances, it's stable right up until it isn't. Now the exhale. Every so often, the trade winds falter. Sometimes they don't just weaken, they reverse and blow west to east for days at a stretch. Forecasters call those westerly wind bursts, and the instant that happens, all that warm water piled against Asia has nothing holding it in place. It starts to slide back downhill toward the east, but it doesn't travel as a visible wave on the surface. It travels underneath as something called a downwelling Kelvin wave, a great slow bulge of warm water moving eastward beneath the surface, taking weeks to cross the ocean. When it arrives off South America, it pushes down the boundary between the warm surface layer and the cold water below. And that boundary, the thermocline, is the thing that controls whether cold water can reach the surface. Push it down deep enough, and the upwelling that normally cools the eastern Pacific starts pulling up water that isn't cold anymore. That is precisely what the July discussion describes. A recent downwelling Kelvin wave deepened the thermocline and raised temperatures in the eastern Pacific. The subsurface heat index, a measure of how much warmth is stored below the surface, weighting increased. That word, weighting, is the important one. What's under the surface right now hasn't finished arriving yet. And here's where it becomes more than an ocean story. Because the ocean and the atmosphere are locked together, and once the exhale starts, the air begins to answer. Warm water makes air rise. Rising air makes thunderstorms. In a normal year, the biggest engine of rising air on Earth sits over Indonesia, where all that warm water was piled up. Move the warm water east, and the engine moves east with it. The July discussion notes exactly that. Convection enhanced over the central and east-central equatorial Pacific, suppressed over Indonesia. The rain machine has physically relocated thousands of miles across the ocean. And when the rain machine moves, so does everything downstream of it, including the jet streams that steer weather across North America. That's the entire mechanism by which a water temperature near the equator ends up affecting whether it snows in Dallas. The atmosphere is answering in other ways too. Low-level winds over the western and central Pacific are running westerly the wrong direction for normal trades. The Southern Oscillation Index, which measures the pressure seesaw between the western and eastern Pacific and is basically a stethoscope on this whole system, has gone significantly negative. NOAA's own summary of it, the coupled ocean-atmosphere system, reflected a strengthening El Niño. Coupled is the operative word. An ocean can warm up on its own and mean very little. When the atmosphere locks in and starts reinforcing it, the event has traction. That's what makes forecasters confident, and it's why that 97% figure exists. Now, I promised you something about February. For decades, the way you graded an El Niño was simple. You took the temperature in the Niño 3.4 box, you compared it to a 30-year average, and the size of that gap was your answer. Half a degree or more above average, sustained, and you had an El Niño. That measurement is called the Oceanic Niño Index, And it's the number that's been quoted in every news story about El Niño for as long as most of us have been paying attention. There's a problem with it. And the problem is that a 30-year average is a fixed ruler in an ocean that isn't holding still. The entire tropical belt has been warming. So when you measure the Pacific against a fixed historical average, some of the warmth you're measuring isn't El Niño at all. It's just the general warming of the whole ocean showing up in your El Niño number and inflating it. Your ruler keeps reading higher and higher, not because the pattern is stronger, but because the baseline underneath it moved. And that started producing genuine forecasting misses. The El Niño of 2023 to 2024 looked, on the traditional index, like a big one. Forecasters expected the southern United States to get soaked accordingly. The atmosphere didn't cooperate. The rainfall response came in weaker than the number said it should be. The index was measuring a strong event. The sky was behaving like a more modest one. So in February of 2026, the Climate Prediction Center changed the ruler. The new official standard is called the Relative Oceanic Niño Index. The idea behind it is almost embarrassingly simple, which is usually the sign of a good idea. You take the same Pacific temperature anomaly you always took. Then you subtract the average anomaly across the entire tropical belt, from 20 degrees south to 20 degrees north. What's left over is the part that's genuinely El Niño the Pacific relative to the rest of the tropics, rather than the Pacific relative to a version of the planet that no longer exists. The consequences of that are not small. In most cases, the new index reads El Niños weaker than the old one did, and reads La Niñas stronger. And because NOAA applied it backward through the historical record, some past events have been reclassified. One example that stopped me: the season Hurricane Helene formed. Under the index in use at the time, there was no La Niña in progress. Under the revised index, a weak La Niña actually was underway, and La Niña conditions are exactly the conditions that raise Atlantic hurricane risk. The signal was there, the ruler just wasn't shaped to show it. Australia and New Zealand had already moved to this index. India has been considering it. Clara Deser, a senior scientist at the National Center for Atmospheric Research, described it as giving a more accurate reading of these events as the oceans keep warming. Phil Klotzbach, the hurricane researcher at Colorado State, has said plainly that he's a fan of it. Now, here's why I'm telling you all this in the middle of a video about a strengthening El Niño rather than at the end. Because the honest thing to say is that the new standard should, in general, make El Niños look smaller than they used to. It's a deflating index. It was designed to strip out exactly the kind of inflation that makes headlines. And this event is still being graded as an 81% chance of very strong for October through December in a category system where very strong means 2 degrees Celsius or above, roughly 3.5 degrees Fahrenheit. Under the stricter ruler, that would rank it among the largest events in the record going back to 1950. That's the part that matters. It isn't a big number because the yardstick got generous. It's a big number after the yardstick got stricter. So let's talk about what a system like this actually does, starting with the thing that's already in motion. Right in the middle of hurricane season, El Niño reaches across an entire continent and puts its thumb on the Atlantic. The mechanism is straightforward once you've followed the exhale. All that new thunderstorm activity over the central Pacific pumps air upward. That air has to come down somewhere, and a lot of it comes down over the tropical Atlantic. Sinking air suppresses storm formation on its own, but the bigger effect is what it does to the winds aloft. It cranks up vertical wind shear, the difference in wind speed and direction between the ocean surface and the upper atmosphere. A hurricane is a vertical structure. It needs to stand up straight to work, stacking its circulation from the sea surface into the high atmosphere so the whole engine can turn. Shear leans on it. It shoves the top of a developing storm sideways off the bottom, and the structure can't organize. Storms that would have become hurricanes in a quiet year end up as ragged clusters of thunderstorms that never get their act together. That's why NOAA's Outlook, issued on the 21st of May, called for a below-normal Atlantic hurricane season. 55% chance below normal, 35% near normal, 10% above. The numbers behind it: 8 to 14 named storms, of which 3 to 6 could become hurricanes, and of those, 1 to 3 could reach major hurricane strength category 3 or higher, winds of 111 miles per hour or more. Compare that to a normal season, which averages 14 named storms, 7 hurricanes, and 3 majors. The forecast top end is roughly where a normal season's middle sits. Colorado State University reached the same conclusion independently, naming El Niño as the dominant factor and pointing to increased wind shear across the tropical Atlantic. And now the part I don't want you to skip. A below normal season is not a safe season. Ken Graham, the director of the National Weather Service, put it about as bluntly as a federal official can. It only takes one storm to make a very bad season. The seasonal outlook is a forecast of how many storms form. It is not, and never has been, a forecast of where any of them go. A quiet year that sends one hurricane into your county is, for you, a catastrophic year. 1992 was a below-average season by named storm count. That was the year of Hurricane Andrew. There's also a wrinkle worth knowing. The Atlantic itself is running slightly warmer than normal, with weaker than average trade winds, conditions that push toward more activity, working against El Niño's suppression. Forecasters explicitly flagged those as competing factors. When two large forces are pulling in opposite directions, the honest answer is that the outcome has more spread in it than usual. And while the Atlantic is being suppressed, the Eastern and Central Pacific basins are being enhanced by the very same setup. NOAA issued active season outlooks for both. The energy doesn't vanish, it relocates. That matters for Hawaii, for Mexico's Pacific coast, and for the moisture that occasionally rides north into the American Southwest. If you've been through a hurricane season on the Gulf or the Atlantic coast, tell me in the comments which year is the one that still sets your standard for how seriously you take these things. I read them, and those answers are usually more instructive than the statistics. Now let's look further out, because this is a system that peaks in winter. El Niño events tend to reach maximum strength between late fall and midwinter, and their effects on North America are most pronounced from late autumn through early spring. The July modeling points toward a peak in late fall or early winter, followed by a gradual weakening through the following spring. Here's the typical winter shape in NOAA's own description. The Pacific jet stream extends and shifts south. The storm track that would normally run into the Pacific Northwest drops toward the southern tier of the United States. That means more storm systems, more precipitation, and often cooler conditions across the southern states: California, the Southwest, Texas, the Gulf Coast, up through the Southeast. The northern tier tends to run warmer than usual, and drier conditions tend to set up over the northern Rockies and through the Ohio and Tennessee valleys. For anyone living with long-term drought in the southern plains or the Southwest, that pattern is genuinely good news, and it's fair to say so. We've seen it work. During the last El Niño winter, drought coverage across the United States and Puerto Rico fell dramatically from more than a third of the country in at least moderate drought at its October peak down to under 20%, with the extreme and exceptional categories nearly wiped off the map. That's not a small thing. That's reservoirs refilling and grazing land coming back. But the same jet stream that ends a drought can drown a hillside. A strong El Niño winter in California doesn't deliver rain gently and evenly across 5 months. It delivers it in trains of storms that arrive back to back on ground that hasn't had time to drain. That's when you get the flooding, the debris flows, the roads that slide off the side of a canyon. During the strong El Niño of 1997 and 98, storms tied to that event killed at least 17 people in California. Drought relief and flood risk are not two different forecasts. They're the same forecast seen from two different valleys. There's a global dimension too. The World Meteorological Organization has warned that a strengthening El Niño raises the odds of both drought and heavy rainfall in different parts of the world at once, along with heat waves on land and marine heat waves at sea. Drought risk climbs across Indonesia and the surrounding maritime region, and in parts of the Amazon, the places the rain machine moved away from. And there's a temperature consequence. A strong El Niño typically shoves global average temperature upward, with the biggest effect showing up in the year after the peak. NOAA's Climate Center currently puts the odds of 2026 ranking among the 5 warmest years on record at roughly 98.5%, while the chance of it taking the top spot outright is under 1%. The interesting year, they note, is 2027. Now, let me give you the honest limits on all of it, because you're going to see a lot of content in the next few months that skips this part. First, you'll hear the phrase Super El Niño. It's everywhere. It is not an official category. The World Meteorological Organization has specifically noted that the term isn't part of standardized operational classification. The actual categories are weak, moderate, strong, and very strong, with very strong beginning at 2 degrees Celsius. Super is a word people reach for when they want a headline. It doesn't correspond to a threshold anyone measures. Second, and this is the caveat NOAA wrote into its own July discussion, in plain language, even the strongest El Niño events do not produce the typical impact everywhere. What a strong event does is tilt the odds. It loads the dice. It doesn't decide the role. Every location has its own local factors, and other patterns in the atmosphere can override the El Niño signal in any given month. We have a very direct demonstration of this, and it's the one I'd point to if you only remember one thing from this section. 1997 to 98 and 2015 to 2016 were both enormous El Niños, comparable in raw ocean temperature. In the first one, California got hammered with rain. In the second, Southern California's winter came in disappointingly dry, and the drought everyone expected to break simply didn't. Same category, same ocean, very different outcome. So when you see somebody confidently telling you exactly what your winter will look like in February because the Pacific is warm in July, they are describing a tilt in probability as though it were a schedule. Ask yourself why they've made that trade. Third, there is genuine forecast uncertainty in the strength itself. Model unanimity about direction is not precision about magnitude. 30 runs agreeing that this event will be large is a meaningfully different statement from 30 runs agreeing on how large. Now, what do you actually do with all this? More than you'd think, and none of it is dramatic. If you're on the Gulf or Atlantic coast, a below normal seasonal outlook changes nothing about your preparation, and the people who issue these outlooks say so every single year. Review the plan before there's a storm with your name on the forecast cone. Know your evacuation zone and your route. Know whether your insurance covers flood, which most homeowner policies do not, and know that flood policies typically carry a waiting period, meaning the day a storm appears in the Atlantic is far too late to buy one. NOAA has also expanded some genuinely useful public tools this season, including an experimental dashboard showing the probability of extreme rainfall a week ahead for more than 60 American cities, and new drone data feeding hurricane models that researchers estimate improves intensity forecast accuracy by about 10%. Intensity forecasting has historically been the weakest link in hurricane prediction. 10% there is a real gain. If you're in the southern tier of the country, especially in California, the Southwest, or along the Gulf, and you're likely to be on the wet side of this winter, the work is the boring kind. Clear the gutters and the storm drains before autumn. Find out whether your property sits in a flood-prone area, which you can check rather than guess. If you're on or below a slope that burned in a recent fire, understand that burned ground sheds water instead of absorbing it, and that a debris flow arrives faster than you can react to it. And if you're in the northern tier, where El Niño winters tend to run warm and dry, that's an easier season for heating bills and driveways, and a harder one for snowpack and water supply next summer. Worth knowing early if your water comes from mountains. None of that requires you to be afraid. It requires you to be a couple of weeks ahead of the calendar, which is a very different thing. So here's where we stand. The advisory is active. The Pacific has begun its exhale, and the subsurface heat that's already crossed the ocean hasn't finished surfacing. The atmosphere has locked in the winds, the pressure seesaw, and the thunderstorms have all moved. 30 model runs, none of them dissenting, point toward an event that competes with the largest of the last century, and they're pointing there under a measurement standard specifically redesigned to be less impressed by warm water than the old one was. And there's a date. The Climate Prediction Center issues these discussions once a month on the second Thursday. The next one lands on the 13th of August. When it does, here's what to look at in this order. Look at the Nino 3.4 value. Is it still climbing toward that 2-degree line, or has it flattened? Look at the subsurface heat index, because that's the fuel gauge, and it tells you whether there's more warmth still in the pipeline or whether the exhale has run out of breath. Look at whether the probability of a very strong event went up from 81% or down. And watch the far eastern box against the western one, because if that lopsided, east-loaded geometry holds through the fall, forecasters will be reading this event against a very specific set of historical analogs. The August update also arrives alongside NOAA's revised Atlantic hurricane outlook, issued right before the season's historical peak in mid-September and October. 2 answers, roughly the same week. Subscribe and turn on the bell, because those numbers are going to be summarized badly in a lot of places, and the difference between a headline and a forecast is going to matter this fall. When the 13th comes, you'll already know which 4 lines to read. The Pacific has taken its breath. Now we find out how long it holds.